Infinity. The very word evokes a sense of awe and wonder, a concept so vast, so boundless it stretches the limits of human comprehension. We grapple with its implications, yet its true nature remains elusive. In physics, infinity pops up in some of the most extreme environments: black holes, the Big Bang, and even the subatomic realm of quantum mechanics. Imagine traveling into a black hole. As you approach, gravity increases, squeezing you from all sides. At the center lies a singularity, a point of infinite density where the laws of physics break down. Here, our understanding of the universe falters in the face of the infinite. But black holes are just the beginning. The universe itself is expanding, and the question arises, will it expand forever? Is our universe infinite, stretching on without end, or is it finite, like a vast sphere with a boundary we cannot see beyond? Even in the subatomic world, infinity rears its head. Quantum mechanics, the theory governing the behavior of particles at the smallest scales, suggests the existence of infinite possibilities and parallel universes. This bizarre, counterintuitive world challenges our very notion of reality. Join us as we journey into the heart of these cosmic mysteries, exploring the role of infinity in physics, and grappling with its profound implications for our understanding of the universe. Black holes stand as some of the most enigmatic objects in the cosmos. These mysterious entities have fascinated scientists and the general public alike for decades, if not centuries. Their very nature challenges our understanding of the universe and pushes the boundaries of what we know about physics and reality itself. Born from the death throes of massive stars, black holes are the remnants of stars that have exhausted their nuclear fuel. When a star reaches the end of its life cycle, it can no longer support itself against the force of gravity. This leads to a catastrophic collapse, resulting in the formation of a black hole. They are regions of spacetime where gravity is so strong that nothing, not even light, can escape their grasp. This immense gravitational pull is what makes black holes so intriguing and terrifying at the same time. The concept of an object with such a powerful gravitational field that it can trap light itself is almost beyond comprehension. Not even light, the fastest thing in the universe, can escape their grasp. This is why black holes appear black. They emit no light, and are invisible against the backdrop of space. The only way we can detect them is by observing the effects they have on nearby matter and light. Imagine a place where the fabric of space-time itself is stretched to its breaking point, a cosmic abyss from which there is no return. This is the reality of a black hole. The closer you get to a black hole, the more extreme the warping of space-time becomes, leading to phenomena that defy our everyday experiences, a cosmic abyss from which there is no return. The boundary surrounding a black hole is known as the event horizon. Once you cross this boundary, escape becomes impossible. The event horizon marks the point of no return, beyond which the gravitational pull is so strong that not even light can escape. As a massive star collapses in on itself, its core implodes, crushing matter into an infinitely small point known as a singularity. This process releases an enormous amount of energy, often resulting in a supernova explosion that can outshine entire galaxies for a brief period. Its core implodes, crushing matter into an infinitely small point known as a singularity. This singularity is a point where densities become infinite and the laws of physics as we know them cease to function. It is a place where our current understanding of the universe breaks down completely. This singularity lies at the heart of every black hole, shrouded by an event horizon, the point of no return. The singularity is a region where the gravitational forces are so intense that they warp spacetime to an infinite degree, creating a point of infinite density and zero volume, shrouded by an event horizon, the point of no return. The event horizon is not a physical surface but rather a boundary in spacetime beyond which events cannot affect an outside observer. It is the ultimate one-way door in the universe. Cross the event horizon and you are doomed to be pulled towards the singularity, your fate sealed by the inexorable pull of gravity. Once inside the event horizon, all paths lead inexorably to the singularity, where the known laws of physics no longer apply. Your fate sealed by the inexorable pull of gravity. The gravitational forces near a black hole are so extreme that they can spaghettify objects, stretching them into long, thin shapes as they are pulled towards the singularity. This process, known as tidal stretching, is a direct consequence of the intense gravitational gradients near a black hole. But what happens at the singularity? Here, our current understanding of physics breaks down. The singularity represents a point where our theories of gravity and quantum mechanics clash, leading to a breakdown in our ability to describe what happens. Here our current understanding of physics breaks down. The singularity is thought to be a point of infinite density, where the laws of general relativity, our best theory of gravity, no longer apply. This breakdown suggests that our current theories are incomplete and that a new, more comprehensive theory is needed. The singularity is thought to be a point of infinite density, where the laws of general relativity, our best theory of gravity, no longer apply. This has led scientists to search for a theory of quantum gravity that can reconcile the principles of quantum mechanics with those of general relativity. Where the laws of general relativity, our best theory of gravity, no longer apply. It is a place where the known universe surrenders to the infinite. The existence of singularities poses a profound challenge to physicists, as they represent a breakdown of our current theories. It is a place where the known universe surrenders to the infinite. The existence of singularities poses a profound challenge to physicists. They represent a breakdown of our current theories, hinting at a deeper, more fundamental understanding of the universe that remains elusive. The existence of singularities poses a profound challenge to physicists. They represent a breakdown of our current theories, hinting at a deeper, more fundamental understanding of the universe that remains elusive. The study of black holes and their singularities offers a tantalizing glimpse into the unknown. They represent a breakdown of our current theories, hinting at a deeper, more fundamental understanding of the universe that remains elusive. The study of black holes and their singularities offers a tantalizing glimpse into the unknown, a realm where the infinite may hold sway, hinting at a deeper, more fundamental understanding of the universe that remains elusive. The study of black holes and their singularities offers a tantalizing glimpse into the unknown, a realm where the infinite may hold sway. It is in this realm that we may one day find answers to some of the most profound questions about the nature of reality. The study of black holes and their singularities offers a tantalizing glimpse into the unknown, a realm where the infinite may hold sway. It is in this realm that we may one day find answers to some of the most profound questions about the nature of reality. The quest to understand black holes is not just a scientific endeavor, but a journey into the very heart of the cosmos, a realm where the infinite may hold sway. The quest to understand black holes is not just a scientific endeavor, but a journey into the very heart of the cosmos. It is a journey that challenges our perceptions, expands our horizons, and ultimately brings us closer to understanding the true nature of the universe. Singularities are not merely confined to the hearts of black holes. These enigmatic points where density becomes infinite and the laws of physics as we know them cease to function are among the most fascinating and perplexing phenomena in the universe. They represent a boundary beyond which our current understanding cannot penetrate, a frontier of knowledge that challenges the very foundations of modern science. They are also thought to have played a crucial role in the very birth of our universe. The concept of a singularity is not just limited to the mysterious interiors of black holes, but extends to the origins of everything we see around us. The early universe, in its nascent moments, was a place of unimaginable density and temperature, a singularity from which all of space and time emerged. According to the Big Bang theory, our universe originated from an infinitely dense and hot state, a singularity that contained all the mass and energy that would eventually form galaxies, stars, planets, and even life itself. This initial singularity is a cornerstone of cosmological models, providing a starting point for the expansion and evolution of the cosmos, a singularity that marked the beginning of space and time. This moment, often referred to as the Big Bang, is not just a point in space but a moment in time when the universe began to expand from an infinitely small, infinitely dense state. It is the ultimate origin story, a moment of creation that set the stage for everything that followed. From this singularity, the universe expanded and cooled, giving rise to the galaxies, stars, and planets we observe today. The process of cosmic evolution from the hot, dense beginnings to the vast, structured universe we see now is a testament to the incredible power and complexity of the forces at work. As the universe expanded, it underwent a series of transformations, each stage building upon the last, leading to the rich tapestry of cosmic structures we observe. The Big Bang singularity, like those found within black holes, represents a point where our current laws of physics break down. In these extreme conditions, the familiar rules that govern the behavior of matter and energy no longer apply. General relativity, which describes the gravitational forces at play, and quantum mechanics, which governs the subatomic world, both fail to provide a complete picture of what happens at a singularity. It is a realm of extreme energy and density, where the very fabric of space-time is torn apart. In these conditions, the gravitational forces become so intense that they warp space and time to an infinite degree, creating a point of infinite curvature. This tearing of space-time is a dramatic illustration of the power of gravity and the limits of our current understanding. The concept of a singularity, a point of infinite density, is difficult to grasp. It defies our everyday experiences and challenges our ability to visualize such extreme conditions. The idea that all the mass of a black hole or the entire universe could be compressed into an infinitely small point is a profound and unsettling notion, one that stretches the limits of our imagination. It challenges our intuitive understanding of the universe, suggesting that there are realms where the laws of physics as we know them no longer apply. These singularities are places where our current theories reach their breaking point, indicating that there is much more to learn about the fundamental nature of reality. They serve as a reminder of the limitations of our knowledge and the vastness of the unknown. However, it is important to remember that singularities are theoretical constructs. They are predictions of our current theories, mathematical solutions to the equations of general relativity, but we have yet to directly observe them. These predictions, while compelling, remain speculative until we can find a way to test them through observation or experiment. They are predictions of our current theories, but we have yet to directly observe them. The challenge of observing singularities lies in their very nature. They are hidden behind event horizons beyond which no information can escape. This makes them incredibly difficult to study, leaving much of their nature shrouded in mystery. Some physicists believe that quantum mechanics, the theory governing the subatomic world, may hold the key to understanding singularities. Quantum mechanics introduces a new set of principles that could potentially reconcile the contradictions between general relativity and the behavior of matter at extremely small scales. By applying these principles, we may be able to develop a more complete theory of singularities. Quantum effects, such as quantum gravity, may prevent singularities from forming, smoothing out the infinite density and avoiding a breakdown of physics. These effects could provide a mechanism for resolving the paradoxes associated with singularities, offering a way to understand how the universe can avoid the infinite curvatures predicted by classical theories. However, a complete theory of quantum gravity remains elusive, leaving the true nature of singularities an open question. The search for such a theory is one of the most important and challenging quests in modern physics, a journey that promises to deepen our understanding of the universe and its most extreme phenomena. Until then, singularities remain one of the greatest mysteries of the cosmos, a tantalizing glimpse into the unknown. Section 4, Quantum Mechanics, Uncertainty and Infinite Possibilities. Quantum mechanics, the theory that governs the behavior of particles at the smallest scales, is a strange and counterintuitive realm. It challenges our classical understanding of the universe, and forces us to rethink the very nature of reality. Unlike the predictable world of classical physics, quantum mechanics introduces a level of unpredictability and randomness that can be both fascinating and perplexing. It is a world where particles can exist in multiple states at once, where uncertainty reigns supreme, and where the very act of observation can influence the outcome of an experiment. This phenomenon is not just a theoretical curiosity. It has been experimentally verified countless times, making it one of the most robust theories in modern physics. One of the most bizarre aspects of quantum mechanics is the concept of superposition. Imagine a world where a single particle can be in multiple places at the same time, or where it can spin in different directions simultaneously. This is not science fiction, it is a fundamental aspect of quantum reality. According to this principle, a particle can exist in multiple states simultaneously until it is measured. The act of measurement forces the particle to choose a single state, collapsing its wave function. This collapse is instantaneous and seems to defy the classical notion of cause and effect. For example, an electron can be in two places at once, spinning in both directions simultaneously, until an observation is made, collapsing its wave function and forcing it to choose a single state. This phenomenon has been demonstrated in numerous experiments, such as the famous double-slit experiment, which shows that particles behave differently when they are being observed. This inherent uncertainty in quantum mechanics has profound implications. It suggests that the universe at its most fundamental level is not deterministic, but probabilistic. This means that instead of a single predictable outcome, there are multiple possible outcomes, each with its own probability of occurring. It suggests that at the subatomic level, the universe is not deterministic, but probabilistic. This probabilistic nature is not just a limitation of our measurement tools but a fundamental aspect of reality itself. It challenges the classical idea that if we know the initial conditions of a system perfectly, we can predict its future with absolute certainty. Instead of a single predictable outcome, quantum mechanics presents us with a range of possibilities, each with its own probability of occurring. This has led to the development of various interpretations of quantum mechanics, each attempting to explain this strange behavior in different ways. This probabilistic nature of quantum mechanics leads to the mind-boggling concept of infinite possibilities. If particles can exist in multiple states at once, and if the universe is fundamentally probabilistic, then it is possible that every quantum measurement spawns a new universe, each representing a different outcome. This idea is encapsulated in the many worlds interpretation. If particles can exist in multiple states at once, and if the universe is fundamentally probabilistic, then it is possible that every quantum measurement spawns a new universe, each representing a different outcome. This interpretation suggests that there are an infinite number of parallel universes, each constantly branching off from one another with every quantum event. This is the essence of the many worlds interpretation of quantum mechanics, a theory that suggests an infinite number of parallel universes, each constantly branching off from one another with every quantum event. It is a mind-bending idea that challenges our understanding of reality and opens up a realm of infinite possibilities. Section 5. The Expanding Universe, a Dance with Infinity. The universe is not static, it is expanding. This groundbreaking discovery made in the early 20th century revolutionized our understanding of the cosmos and raised profound questions about its origins and ultimate fate. The expansion of the universe is a consequence of the Big Bang, the cataclysmic event that brought space and time into existence. Imagine the universe as a balloon being inflated. As the balloon expands, the distance between any 2 points on its surface increases. Similarly, the space between galaxies is stretching, causing them to move apart from one another. This expansion is not like the explosion of a bomb where fragments are propelled outward through a pre-existing space. Instead, it is the fabric of space itself that is expanding, carrying galaxies along for the ride. The expansion of the universe has profound implications for the concept of infinity. If the universe is infinite, then it has always been infinite, even at the moment of the Big Bang. The Big Bang did not occur at a single point in space, rather it happened everywhere at once, filling all of space from the very beginning. On the other hand, if the universe is finite, then it has a boundary, an edge beyond which there is nothing. What lies beyond the edge of a finite universe? These are questions that continue to puzzle cosmologists. If you enjoyed this exploration of infinity, make sure to subscribe for more fascinating content.